Hi there, hope you're doing well. I'm glad you're here along with me to learn a little bit more calculus as we begin the calculus portion of our IB Math SL syllabus. Now, we've looked at finding limits so far, what a limit is for a function and how you find that limit, and that idea is going to be applied here as well. What we're going to get into today, though, is something that you're going to be spending almost this entire chapter on that we're currently working on, and that is working on derivatives. Now, in calculus, there are two basic branches of calculus that we're going to be focusing on, well, because there's two of them that exist, and those two things are called differential calculus and integral calculus. And the one that we're working on in this chapter is going to be called differential calculus. And whenever you're working with differential calculus, pretty much what you're doing is you're finding derivatives. Now, I'll tell you this, and we'll talk more about actual real-world applications of this as we go on. But derivatives are great for finding what's called an instantaneous rate of change. An instantaneous rate of change. And I'll refer to that a little bit more later on in the video. Two goals here. First is that you're going to learn to find the slope of a line that is tangent to a curve at a given point. And then you're going to learn the definition of the derivative of a function. I'd like to begin our lesson with a little investigation into how you find the slope of a line that is tangent to a curve at a given point. Now, a definition is required first. What is a tangent line? You might recall when you were studying circles in geometry that a tangent line was a line that intersected a circle at exactly one point, didn't go through the circle, just touched it at exactly one point and went on. And in calculus, we're going to refer to tangent lines as well. What we're going to do is, instead of having tangent lines to circles, is we're going to have tangent lines to curves, all right, which these curves are going to be graphs of functions. And still, as they were when you were studying circles, a tangent line intersects a curve at exactly one point. Now, I've set up a little drawing here in GeoGebra to illustrate exactly kind of what that tangent line is going to look like. So I've got this point P here, and at that point P, you see that this line touches the curve at least once. And I've made it so that I can move that point P around a little bit, and you see how the tangent line changes as I move that point P around. Okay? And at every point on the curve, the tangent line has a different slope. And what we're going to be able to do is we're going to be able to figure out a way to calculate what the slope would be at any particular point on that curve. The slope of the tangent line at any particular point on that curve. Now, why do we care about doing that? Well, I said one of the things earlier that calculus is good for, and differential calculus in particular, is for finding what's called an instantaneous rate of change. And a slope is a rate of change. And if you can find the slope at a given point, you're finding an instantaneous rate of change. An idea we'll explore in another lesson a little bit further. All right, now here's what we have to think about when we're trying to find the slope of that tangent line. Whenever you're trying to find the slope of a line, it takes 2 points to find the slope of that line if you're going to use the typical slope formula that you make, right? But the problem is here that we only know the coordinates of one point that are on this tangent line. We know it goes through this point P right here, but we don't know any other points that it goes through. So how can we find the slope without using, or with using only one point? All right, there's going to be a process that we're going to go through. I'm going to make this tangent line disappear, and I'm going to start discussing with you what are called secant lines for a moment. And I made a secant line up here. Now, a secant line is simply a line that intersects a curve at 2 points. Well, 2 or more points depending on the kind of curve. With a circle, is a line that intersects a circle at least, or at 2 points, if you remember that definition from your geometry days. And so here's a secant line, and what I did was I have it going through that same point P that we're trying to find the slope of the tangent at, and then I created another point Q on the curve, and I made the secant line go through those 2 points P and Q. And because it goes through 2 points, we're going to be able to find the slope of that line. Now, I'm going to derive a little formula for you here that's going to be very important to us later on in the lesson. And I would like you to write this down. What we're going to do is we're going to pretend that this point P, it's kind of hard to see the P there, but it is there. This point P has generic coordinates. And we'll just say that its generic x coordinate is x. And then we're going to say that its y coordinate is f of x. All right, just a result of plugging in this coordinate into the function f. Okay, and then what I've done is I've created a point Q that is h units away from point P horizontally. So here's what I mean by that. If we were to try to find the rise and the run between this point P and this point Q, the run would be h is what I'm trying to say. I want a horizontal separation of h units here, which is just a generic number. And so that would make the coordinates, the x coordinate of this point Q, h units greater than this x coordinate, right? So in other words, we could say it's x plus h. And then the y coordinate for that point Q would simply be whatever you get from plugging in x plus h into the function f. So it would be f of x plus h. All right, now what I'm trying to do, I think I said, was I'm trying to find the slope of the secant line, and I'm going to use the coordinates of these points P and Q that I created to do that. Remember, you can find the slope by finding the difference in the y coordinates over the difference in the x coordinates, or y2 minus y1 over x2 minus x1. So let's go ahead and do that with these. Let's say this is my point 2, this is my point 1. So y2 minus y1 would be f of x plus h. That's y2 minus y1, which would be f of x. And then we'd have to put that over the difference in the x coordinates, with the first x coordinate being x plus h. Sorry, the second x coordinate, I suppose, is x2. And then the x1 would be, well, x. That was the x coordinate for point P, correct? All right. And then I'm going to do a little simplification with that formula. Let me bring that down here. There's nothing I can do to simplify the numerator. It's going to remain as is. But in the denominator, if I have an x plus an h and minus an x, those two x's end up canceling one another out, basically, and I'm just left with an h. Now, this is what I want you to write down right here. This thing is called a difference quotient. But all it's really doing here, as complicated as it's looking, is it's helping us find the slope of this secant line. All right, we'll come back to that momentarily. Now let's zoom out again so I can start showing you something here. You see how we found the slope of the secant line, and I want you to see that the secant line, I'm writing its slope right here. Currently the slope of the secant line is 2. Put the tangent line back on the graph. And you can see right now that the slope of the tangent line is 1.1. Now, I don't want you to pay attention to that slope so much right here, but I do want to show you something here. What I'm going to do is I'm going to decrease the horizontal distance h between those points P and Q. All right, remember the other day when, or in the last video that we watched when we were finding limits, okay, where you would find the limit of a function at a given point by continually getting closer and closer and closer and closer and closer and closer to that point from one side and from the other side of that point along the curve? Well, that's kind of what I'm going to do right here. Now, watch this. I'm going to decrease the value of h, and as I decrease the value of h, you see the secant line changing because the location of point Q is changing. Now, point P is staying in place. And the closer point Q gets to point P, the closer and closer that secant line comes to matching up with the tangent line. All right? Until, notice I'm 0.1 units away and they almost match up. Well, as soon as h is 0, or in other words, as soon as point Q and point P are exactly in the same place, that secant line and the tangent line become the exact same line. Now, what am I talking about then? If I approach point P from the right side, the slope of the secant line becomes the slope of the tangent line. And what I'm saying to you then is if I take the limit of that slope as h approaches 0, okay, that distance between the 2 points P and Q, that gives me the slope of the tangent line eventually. Now, just a curious thing here, why does it say the secant slope is undefined instead of 1.1? Well, simply because it's measuring the slope of the secant from points P to Q, but they're exactly the same point, so you get 0 over 0, and that's undefined, right? Now, remember a moment ago when I told you the way you find the slope of the secant line through points P and Q is with this big difference quotient expression right there. And then I showed you that if you take the limit of the slope of the secant line, it gives you the slope of the tangent line. So I can say that the slope, the tangent slope, is equal to the limit as h approaches 0, the distance between points P and Q, of that difference quotient right there. All right. Now, really the point is we use the slopes of secant lines in order to find the slope of the tangent line. Now, let's talk a little bit more about the slopes of tangent lines. And what I want to do is I want to tie in the slope of a tangent line with what we call the derivative of a function. And here is the main takeaway that I'm going to want you to get from this video is what is the derivative of a function? Okay, well, it is tied into that whole slope of a tangent line thing that we were talking about. There's a portion of the picture that we were just looking at. I'm going to label some things. And the things that I've labeled so far are threefold. I labeled the curve as a function f of x, and I just went ahead and labeled this as the tangent line, and this point P as the point of tangency. And it turns out that whenever you find the slope of a tangent line, well, that's what we call the derivative of a function. The value of the slope of a tangent line is the derivative of a function f of x. The tangent slope and the derivative are the same thing. All right, hopefully you get that in your head. Now, I said the differential calculus was for finding instantaneous rates of change, and I said if you could find the slope of the tangent line at a given point, you'd be finding an instantaneous rate of change. So that's why that's what the derivative is defined. Well, corresponds with, I should say, because the definition that I'm going to show you for a derivative is a little bit different. Now, remember the way you find that slope of the tangent is by using that difference quotient that you use to find the slope of the secants and taking the limit as this second point gets closer and closer and closer to that point P, the point of tangency. All right, or in other words, you used this expression. The limit as h approaches 0 of f of x plus h minus f of x over h. That's how you find the derivative of a function. Now there's some notation that you need to learn, and you'll see it over and over and over and over again. Whenever you want to show that a quantity is the derivative of a function, or that, well, I'll leave it at that for now, the notation that you use is you use prime notation, they call it, where you put an apostrophe after the name of the function, but you read it as prime. This is f prime of x, and f prime of x means the derivative of function f at point x. Okay, now the last thing I want to do in this video is demonstrate how you can use that limit in order to calculate the slope of a tangent line, okay, just so that you see that it actually works. So let's go forth with an example of how you find derivatives using this definition of a derivative, which was our second goal, by the way, in this video. So here are the directions for the example that we're working on. It's telling us to use the definition of derivative that we just learned in order to find the derivative of function f that's given here, and then hence find the slope of the tangent line at the given value of x. So we'll find the derivative of this function here, and remember a derivative corresponds with the slope of a tangent line at a given point x, and then we can in turn, once we find that, find exactly what the slope of the tangent line for that curve would be at the point where x is equal to -1. Okay, now I'm going to get the directions off the screen so I've got more room, because this requires quite a lot of room in order to do all this work. Finding the derivative. Notation is super key here. Remember, whenever you're finding a derivative, the notation you use to indicate that you're finding a derivative is the prime notation. You write it as f prime of x, and then remember that it involves finding a limit. The limit as h approaches 0 of f of x plus h minus f of x over h. Now, at this point, you've never seen how to simplify a big expression like this. All right. Now, I'll tell you that we're going to hold off on the limit part until the very end, and what we're going to do is we're going to simplify this difference quotient. In order to do that, we've got to make some substitutions. We've got to substitute the value of f of x plus h here and the value of f of x right there, and we're going to get those from the f of x that was given to us. Now, all f of x plus h is, remember, is this function f when you replace the input with x plus h. So in other words, we're going to replace this x with an x plus h. This is how that's going to look. All right, rewrite that limit expression, and then the f of x plus h would simply be 1/2 times x plus h squared. And then from that, we're supposed to subtract the original function f of x, so we'll just put minus 1/2 x squared. And then in order to simplify this numerator, we're going to need to go ahead and square the x plus h next in order for us to ultimately be able to do the subtraction that's up there. All right, so this 1/2 x plus h squared. Let's leave the 1/2 alone. You know how to square a binomial. You know that squaring x plus h will give you x squared plus 2xh plus h squared. And then we'll copy down the minus 1/2 x squared. And we'll copy down the denominator still as well. Now, I understand this looks big and long and complicated, but things are going to work out nicely in this next couple of steps. I promise to make it look much less complicated. The last thing we got to do before that can happen is we've got to distribute this 1/2 to this whole trinomial thing right there. So we'll get a 1/2 x squared plus xh plus 1/2 h squared. And then we've still got the minus 1/2 x squared at the end, and still got the over h. And a couple of things are about to happen now to make this nice. First of all, notice that the first term and the last term of the numerator are opposites of one another, so we can go ahead and cancel out the 1/2 x squareds. And secondly, notice that every term remaining has an h. Now what I'm going to do is I'm going to factor h out of the numerator, so that the numerator will become h times x plus 1/2 h. And then what the factoring, of course, helps me do is cancel out the h that's in the denominator, so this is no longer even a fraction. We're just trying to find the limit as h approaches 0 of x plus 1/2 h. And then since there's no h in the denominator anymore, all we have to do in order to find that limit is simply substitute 0 in place of h. And if you substitute 0 in place of h, you're going to get x plus 0 or x. Turns out the derivative of this function, 1/2 x squared, is simply x. Right there. Now, we found the derivative of the function, and most of the time the derivative of one function is simply another function. This is just the line y equals x, it turns out. Now remember, the next part of our job was to find the slope of the tangent line of the original function when x equals -1. Okay, well, I'm going to explain a couple of things here. First of all, when it says x equals -1, it's trying to tell us where the point of tangency is. And we could find the coordinates of the point of tangency simply by plugging in -1 into the function f. All right, so we're going to find f of -1, which is equal to 1/2 times -1 squared, or in other words, 1/2 times +1, which is just 1/2. That means the point -1, 1/2 is the point of tangency. And then what is the slope of the tangent at that point? The way we're going to find the slope of the tangent line at that point, -1/2, is we're going to go ahead and plug in -1 into the derivative function that we got. We're going to find out what f prime of -1 is. So f prime of -1 is simply going to be equal to -1, it turns out. All right, so -1 is the slope of the tangent line at x equals -1, and the derivative of the function was simply f prime of x is equal to x. Let me show you that that worked. And in order to show you that, I want to show you the graph. Now, you can see kind of the equation for the graph that I made right here. Y is equal to 0.5x squared or 1/2 x squared. That's what this parabola represents. And I went ahead and graphed the point of tangency that we were most interested in, the point -1, 1/2. And what I want to do is show that the slope of the line that's tangent right there is going to be -1, as we found using the derivative a moment ago. Now with GeoGebra here, I'm able to draw a tangent line. If I just go to this little section right there, pick tangent, and then I'll click on the curve that I want a tangent line for and the point that I want it at. There's the tangent line. And then I can show you the slope of the tangent line at that point was -1. If I use this little slope tool right here, just pick the line that I want to find the slope for. And you can hardly see that. Let me zoom in a little bit. But it says the slope is -1. See that right there? Okay, great. So you've seen how to use secants in order to find the slope of a tangent line, and you learned the slope of a tangent line is the derivative of a function. And you've learned how to use the definition of a derivative in order to find the derivative of a function and to find the slope of a tangent line at a given point. Lots of info. We're going to need to do lots of practice with this in class. Hope this has been helpful for you, though, and that you understand a little bit about derivatives now. Thank you for your attention, guys. See ya.